I'm starting this experiment at 14:20 in the afternoon, and as the experiment proceeds, you'll know why I need to know this time. So what have I got? Well, I have a rod of ice which has been made in my freezer overnight, solid, and hanging over it I've got a wire, and on each end of the wire I've got a mass which corresponds to a force of 5 newtons on either side. So 500 grams there, 500 grams here, so each side 5 newtons. Now at the start the wire is resting on the ice, but what should happen as time passes is, because the wire is quite narrow, the pressure under the wire on the ice will be high, and high pressure will lower the freezing point of ice. That means that the ice just below the wire will melt more rapidly than the ice which is under normal room pressure on either side. The wire should then dig itself into the ice, which will then refreeze above it, and we'll return sometime later this afternoon to see how it's getting on. You may now see why we needed to know the time at the start of this experiment. It's now, well, almost 1500 hours. In other words, 40 minutes since the experiment started. And you can see that the wire has cut itself into the rod of ice. How far? Well, at least a centimetre. And more than that, at the top here, the ice has refrozen above when the pressure has been reduced to atmospheric pressure again, and it's a perfectly smooth join over there. So the experiment has been really very successful, but what's actually happening here? Well, when ice melts, heat energy is needed. When water freezes, heat needs to be taken away from the water. Think of what's going on in your fridge or your freezer particularly. You are using a method of extracting the heat. And here, the heat is extracted by it flowing by conduction down the two sides of the metal wire to those big lumps of metal, which you can't see in this shot, but the lumps of metal will get slightly warm. And therefore, if we'd used string, it wouldn't have worked, because we couldn't have conducted the heat away down through the string, because string is a pretty poor conductor of heat energy. And finally, what about large-scale effects of this experiment? In other words, do ice skaters skate on water, or do they skate on ice? In other words, is the pressure beneath the blade of the skate big enough to melt the ice? And the answer is no, it isn't, nowhere near. However, glaciers are a different matter. The enormous weight of a glacier on the rock at the base is enough to melt some of the ice underneath the glacier and turn it into water. And you will have seen, if you go and visit a glacier, that water is running out underneath the front of a glacier.